So, in this module we will talk of two other kind of defects that are possible in FCC materials. So, one of them is called Frank partial. So, this is also a partial Berger vector, but again this is not glissile, meaning it does not glide, and the other one is a very different kind, but again related to the stacking fault that we see in the FCC system. So, let us start with the Frank partials. What are Frank partial dislocations? Now, if you remember, we had the Thomson's tetrahedron like this, where we had A, B, C, D, and opposite to A at the center we had alpha, opposite to B at the center we had beta, opposite to C we had gamma, and just below D we have delta. Now, let us say there is a Berger vector which goes from A to alpha like this, or D to delta, meaning it is perpendicular to the plane ABC, but it is connecting to the point D. So, that kind of Berger vector is called a Frank partial dislocation. Now, which plane does this partial dislocation lie on? Any of the 111 plane? No, it does not. You can see this is lying normal to one of the 111 plane, and it is not lying on any of the other 111 planes. So, even without knowing the line vector, we can say that it does not lie on any of the 111 vector. So, let us look at what is the magnitude of this Berger vector. So, let us say if ABC was the (111) plane, so our Berger vector is perpendicular to it. So, its direction will also be 111, and therefore, it is of this kind. So, the magnitude is A by 3 111, and it can be represented by A alpha or B beta or C gamma or D delta. So, this is a Berger vector which does not, now the any of the 111 direction does not lie on any of the other 111 planes, which is a fact, and therefore, we can clearly say that these Berger vectors, let me call it Frank partial, does not lie on any 111 plane, and hence is it glissile or sessile? Glissile meaning it can glide, sessile meaning it cannot glide. So, it is sessile, hence it is sessile. It cannot glide. The other partials that we were talking about, now if we have given this a name, so it is important that we give a name to the other partials. The other partials that we have been talking about so far, just to keep things in perspective, not can be, are called. Which are of the type A by 6 112, Shockley partials. So, in FCC we have two kinds of partials, Shockley partials which are glissile, which we saw are of the form A by 6 112, and we have Frank partials which are sessile and which are of the form A by 3 1 1 1. But one must keep in mind that it can still climb, meaning at high temperature this dislocation can still contribute. And just to again bring back our Thomson tetrahedron, if you remember I said this is your, from this drawing you should understand that our partial is like this. So, if this is the 1 1 1 plane, this is the Berger vector from center of this plane to the tip of this plane, and that is called a Frank partial dislocation. So, we will come back to this slide, and like I said this can still climb, and this is where it can contribute to deformation only at high temperature. So, that was Frank partial. Now, the other kind of defect that is possible in FCC, they are called twin boundaries. You remember we talked about 1 1 1 plane and they have 3 possible layer stacking, what we called as ABC stacking. So, let us visit that again. Here we have this 1 1 1 plane and the 3 different layers are shown in 3 different colors. So, you have one blue colored 1 1 1 plane, and you have then red colored 1 1 1 plane, and then you have a green colored 1 1 1 plane over here. And if you stack them, that is when we get the ABC type of stacking. At that time we were looking from the 1 1 1 direction. Now, let us try to, so if this is a 1 1 1 plane, so we were looking at it from top. Now, let us try to look at it from, let us say, in this direction, meaning what we are looking at are the packed atoms and normal to this. So, what you will see is something like this. So, you have one layer A, then you have B, then you have C, again you have A, again you have B, and again you have C. So, you can see ABC. And what is the, how do we say that these are different and at what stage it becomes same? So, that you will be able to identify when you put a line. So, if you put a line over here, you would see that this particular layer does not lie just on top of it, it is a little shifted. C is also a little shifted, and by the same amount when the 4th layer is shifted, it comes back to the original position A, and that is what we meant when we said ABC packing. From the top view which was the 1 1 1, we looked at it with respect to what were the possible sites or the gap or the positions where it could have occupied, and here we are looking at from a different perspective. So, these are the ABC planes, sorry, the ABC stacking. Again I am showing you ABC. Now, what happened when we had 2 partials or a one dislocation splitting into 2 partials? So, the 2 partials moved and we saw that somewhere that layer became or generated a stacking fault, meaning in that region you did not have ABC kind of packing. So, right now if it is ABC, somewhere in between that region the stacking fault was generated. And how was that generated? By displacement of A by 6 1 1 2 type of magnitude vector. So, first thing that here you can see this B and B are matching. So, what we said that the atoms are shifted. Now, let us shift the A layer by A by 6 1 1 2 in this direction. Now, what do you see? That it has moved a little bit, and then what should become the stacking? Now, it should not be ABC. The A layer should now become B, and similarly the other layers on top of it, they should keep shifting onwards, and therefore, this will be a new type of stacking ABC, B, and then again it will continue. So, there is a stacking fault created which we said earlier, which could be formed due to 2 partials. So, you can say there is one partial here, there is another partial over here. So, this stacking has been formed, let us assume, because there are 2 partials. So, this one partial is over here, one another partial is over here, and in between this is the region where we have this stacking fault generated. So, this is leading to this partial or some way or the other, this is stacking generated. Now, this stacking fault is stable, even if you have just one layer of stacking fault, it is stable, and that is why a partial dislocation is possible in FCC system. Now, let us take it further. Let us assume that each layer is displaced by this amount A by 6 112 in the direction 112. So, after this B layer has been pushed, again C layer will be pushed, and again A layer will be pushed. What do we get? We get a structure something like this. Now, what is this structure? If you look at it carefully, you would see a symmetry over here. So, there is a reflection plane somewhere here, and about that reflection plane there is similar kind of atoms here and similar. So, it would look like it has flipped onto this side. Let me redraw it. So, you can see it again. Now, you will see that this is a layer forming like this and over like this, and again here the colors have not been changed after the displacement. So, this does not represent a B layer anymore, it does not represent a C layer anymore, it is just the originally B layer, original C layer, original A layer. Now, it has been moved to a very different place. What will be the new sequence? We will come to that in a moment, and in fact, you should be able to call it from here, because now if this we remember this is A, this is B, this is C. So, this is reflection, if this is C, this should also become B. If this is reflection, then this should become A. So, this has now become, this is the plane about which we are seeing a reflection. So, whatever you see over here, you would see a reflection over there, and therefore, you get a structure like this. This is why it is called a twin boundary. So, this it is like it is as if about this line there exists a twin, whatever you have over here you would see over there. So, this is called a twin boundary, and this is an additional mode of deformation for many metals and alloys. Now, let us look at this twinning with respect to the 111 direction. Now, we are looking at the 111 direction, 111 planes from the 111 direction. So, this is now 111 plane, and we are looking, this is the 111 direction. Now, with respect to that, right now you have only 3 layers A, B, C, and the other 2 layers should be B and A when you put one top of it. So, at the top of C what should come? If we are talking about reflection, then there should be a B layer, and you can see that the here I have drawn it using red color, which is for the B, and it lies just above the B. So, this B and this B, they are overlapping. Now, the next layer when I add, which is A layer, which is blue color, which is also the A layer. So, again you would see that this blue layer is overlapping with the blue layer on the bottom, and it is indeed a twin. So, note that ABC BA arrangement, which implies reflection about C layer. So, we have a reflection or a twin around this layer, and hence we have what we call as twinning, and this is when you are deforming, you have in FCC materials there can be deformation by dislocation slips as well as because of twinning, and both of them are competing phenomena. Next, there would be some energy associated with twin boundaries, energy associated with stacking fault energy, but we also know that both of them are being formed because of stacking fault. So, there must be some relation, and there is indeed a relation. So, let us look at what is that relation. So, first let us talk about a simple stacking fault which is generated due to partial dislocations. So, this is ABC, ABC. Now, over here one of these layers is moved by A by 6 112. Okay, let me write it more clearly with a different pen. So, what will be the new sequence, and it is, let us assume that it is the top layer which is being moved. So, everything will move beyond that. So, first let us write what will happen. So, first these 3 layers remain as it is. A will now become what? A will become B, and now after that the sequence remains same. So, after B comes C, after C comes A. So, this would be the sequence, and this is where we have our stacking fault. So, this is for due to partials. A stacking fault region has been generated. On the other hand, let us talk about the layers that are formed when we have a twin boundary formed. So, here also we have displacement by A by 6112, but it is not only for one layer, it is in fact for each layer. And in the end what we get is a structure like this, which we have seen earlier, and this will become the reflection plane. So, C, beyond this it will become B, beyond this it will become A. So, it is a, in other words you can say the sequence here becomes negative. It was going A B C, now it becomes C B A. So, this is what we see, it is now becoming . Now, let us understand why should there be any energy associated with this. Here, as we said earlier, that atoms of other kind are coming closer than they are comfortable with. It is this that leads to increase in energy. So, here for example, if you look at it, the next nearest neighbor is B and B. Over here the next nearest neighbor is A, over here it is C. So, it is not the same type of atom or the same position of the atom, and therefore, the repulsion is weak in here, but when you come over here the repulsion becomes stronger. So, there is same type of these atoms are at the same site in the next nearest position. So, this adds to their repulsion. So, let us say this is B and B. This is showing that there is one layer another over here. Now, there is still one more set of atoms which should not be there, but are still there. So, and this is for example, C and C. So, they are also becoming next nearest neighbor. They do not want to be the next nearest neighbor, they want to be 2 atoms apart. That is what means by what we mean when we say ABC, ABC. But here we see that it becomes next nearest neighbor. So, it becomes C and C. The energy, additional energy because of next nearest neighbor coming together is delta. So, there is a delta energy here, there is a delta energy over here. So, the energy of SFE we can say is equal to 2 delta. Now, let us compare it when in the case of twin boundary. Here when we look at it, there is again something like this forming B and B. So, next nearest neighbor, they are on the same position and they do not like that, they are not happy about it, there is a repulsion, and therefore, there will be some energy associated with it, which is equivalent to delta. Now, what about the other atoms? Here it is A, there it is C, is okay with it, there is no problem. If we go C and A, that is also again okay with it. So, and beyond this anyways it is a regular sequence. So, there should not be any problem. So, in this neighborhood we get only one of those repulsion or the kind of you can say layers pushed together which they do not want to be there. In this case there is only one. So, energy of twin boundary is equal to delta. And when if you look at it, that this delta and this delta should not be different because they are coming from the origin is same. The next nearest neighbor is repulsion is what leads to this delta, and therefore, we can say that E twin is equal to ESFE by 2. So, this is an approximate relation which is found where to be approximately true, again as approximately we derived, as approximately it is true for many of the metals and alloys. So, this is another aspect about the defect which is the twin boundary. So, we will end our lecture over here and we will see you in the next class.